So we will take a look at lab 0, and for that we will be using the Spartan 6 FPGA. The task is to create a pulse signal with a period of 10 microseconds, where one of these pulses will be 1 clock cycle long. So to do this we will be reusing the counter that we made in lab 4, but we will make some slight modifications to it. We won't need the data input and the load function, and also the count should not be output to anything. We'll just use it for setting the terminal count so that can reset the counter again. And we will also be using this TC as the output pulse. If we take a look at the user manual for the Spartan 6, we can see that we can get 3 different clock frequencies: 40, 66.7 and 100 MHz. Both 100 MHz and 40 MHz could be used, but we will take the 40 MHz since that will result in the least amount of hardware. So we got our clock input here. I decided to keep the enable pin and the reset, so that it can either be reset by the user or by this comparator circuit here. So the counter is a 9-bit counter. We upgraded that from a 6-bit, and it will be counting up to 400. When we do that with a 40 MHz input frequency, we will get the 10 microseconds that we need. So when our count reaches this value, we will pull the TC high, and that will reset the counter, so we will start all over again. And while this TC is high, we will also get our output pulse, which will be high for 1 clock cycle, since this is a synchronous reset. So we will take a look at the VHDL code in the ICE software here. First we tell it to use the IEEE standard logic libraries for all the signals and math. Then we start our entity counter, and we create a port with our input and outputs. We have the clock, the enable, and I left the load and the data in here so that I shouldn't change the code down here, but in theory we could just delete that. Then we got our reset and our TC, the terminal count. And I deleted the count output from this because we don't need that. And then we got our end of our entity, and we start the architecture. We create a local signal called count. That is a 9-bit vector. We begin our architecture, and we tell that every time count is equal to 400, the TC should be 1, else 0. Then we start our process, which is sensitive to clock, and we begin. We check if we got a rising edge of the clock. Then we check if our reset is high or if our count has reached the 400 that we decided earlier. If it is, then it should reset, set all bits to 0. Else we will check if enable is low, and it's an active low enable, by the way. If it is, then we will check if we should load some data, and we won't use this actually. And if we don't load, then we will just add 1 to the count, and we will finish this. So this will basically count up until we reach 400 and then reset. And we end the process and the architecture, and that is pretty much all of the code. Then we also got our UCF file. We will route the net clock to V10 on the FPGA. That is the pin that connects to the 40 MHz clock. And the TC, we will route that to H12, which is one of the pins on this input-output connector. Then we will have to pull our load down. The enable should be pulled down as well because it's active low. And the synchronous reset is also pulled down. If we wanted, we could map these to some of the pins as well. and also the data, which I didn't include here. But we could set some data on some of these pins and then load it in if we wanted to. And if we take a look at our RTL schematic, we can see we have the TC output, the data input, which we will not be using, the enable, clock, load and reset. So I just expanded this block here, and if we take a look at the schematic, we can see that it looks pretty much like what we expected. This fat line here is the 8-bit bus for the count, and we got some muxes and some flip-flops, and the count output here is put through these 3 logic gates that will check if 400 is reached, and if it is, we can see it will go to this OR gate, which will reset all the flip-flops. We can see that signal also goes to our output. So I programmed the Spartan 6 board, and we will see if it works. Fix this in here, and we'll need it. So at least there is something. And the peaks seem to line up with the 10 microsecond marks. And the width of the pulse is 25 nanoseconds. And if we take the inverse of that, we get exactly 40 megahertz. So we know that the width of the pulse is correct. And I think this is the best we can do for checking the spacing between them. It is at 1 microseconds per division, and we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. We could try and measure this, but I don't think it will do any better. It says 10.03 microseconds, but the resolution is not that good. So I think that covered pretty much most of it, unless I forgot something, but see ya!